Hi, I'm Stefan Muller, and I'm going to tell you about my paper Static Prediction of Parallel Cost Graphs being presented at POPL this year. Many static analyses for parallel or concurrent programs, such as those that detect deadlocks or race conditions, perform a large part of the analysis not over the source code of the program itself, but over an abstraction of the parallel structure of the code, represented as a graph, variously known as a dependency graph, computation graph, or, particularly when the property of interest is complexity, a cost graph. Nodes in these graphs represent sequential pieces of code, and edges represent dependencies. In this abstract representation, many properties of interest become relatively clear. For example, a cycle in the graph indicates a deadlock, or if two nodes have no path between them, then the corresponding program points may happen in parallel, which may be important information in detecting a data race. In many modern languages, the parallel structure of the program is determined dynamically based on runtime information, which makes it quite difficult to statically determine information about the program's graph. For example, in this classic parallel Fibonacci function, the two recursive calls to fib are performed in parallel using futures, parallel threads that can be touched later to wait for the thread to complete and return the result. The number of times the computation splits like this is, of course, determined by the argument n passed into the function. This is a simple example, but futures are much more powerful and can result in very complex dependency graphs. Static analyses that work by building a computation graph must, therefore, be relatively complex, and must over-approximate the set of graphs that might result from a program in order to maintain soundness. This complex analysis to build the graph must be effectively built from scratch for every new analysis algorithm, whether it's a deadlock detector, a race detector, an analysis for cost bounds, and so on. However, the dependency information collected by many of these algorithms are fairly similar. This paper presents a framework to reason about the set of graphs that may result from running a program, allowing us to analyze a program once to get the graph information. Many different static analyses can then be built from this information. The information is collected in a form that I call a graph type. Graph types are so named because they represent a compact approximation of the set of graphs that might result from running a program, analogous to the way that static types represent a compact approximation of the set of values that might result from running a program. For example, if, in a context where n has integer type, fib of n has integer type soundness ensures that the result will be an integer. In the same way, assigning a graph type g to the program means that g describes a set of graphs that could result from running the computation, a property that's also guaranteed by soundness. The paper first describes the syntax of graph types through several examples. Next, it presents a graph type system for a parallel calculus containing futures, as well as a proof of soundness, motivated on the previous slide. The paper describes an algorithm for inferring graph types for a parallel functional program, building on Hindley-Milner type inference. The algorithm has been implemented for a large subset of OCaml. The implementation was tested on a number of micro-benchmarks, as well as a larger case study of a concurrent web server, and also includes proof-of-concept implementations of several program analyses and transformations that can be done over graph types. Namely, a deadlock detector, an analysis to estimate the asymptotic complexity of parallel programs, and a transformation that can convert some programs written only using futures into programs using only a simpler form of parallelism known as fork-join parallelism. Even without complex analyses, the graph types inferred by the implementation can give useful feedback to programmers, just as types can be helpful in debugging. Consider this program, which calls a function f on each element of a list L and sums the results. It does so in a pipelined fashion so that all of the calls to f occur in parallel. The visualization on the right is produced directly from the graph type by our implementation. While the code is fairly complex, the graph type of the program indicates that the calls to f, represented by g2 in the visualization, do in fact occur in parallel. Now consider a small change to just the underlined portion of the code. While swapping the order of the two addends won't make a difference to the final result, touching the previous future before the next call to f actually sequentializes all of the calls to f, as can also be seen in the graph. The implementation of graph type inference scales well enough that it can be included in compilation. The proof of concept static analyses also show promising results. The deadlock detector correctly finds deadlocks in several complex examples, and correctly identifies others as deadlock-free, including a deadlock-free program that would not be recognized as safe by prior work on deadlock detection. The implementation also correctly identifies the asymptotic complexity of several parallel algorithms. For more details on the graph types, the graph type system, and the other results, I hope you'll watch the full-length talk and read the paper in the proceedings.